Okay, first of all, this is the last time this semester I will give you notes for a lesson. This is the last new material of the semester. A little dance inside, okay? So I'm going to hand things back. Find this, find this, find this. Please use your answer here to find the next one. Use that answer to find the next one. Okay, go start from scratch. Okay. You know, guys, I'm worried about you. Can you see okay right now? Yes. Please? Yes. No? Okay. One more time. Ooh, this. You didn't get explained the package because I don't have this.
The triangle thing, where you have to like go down, this way, and that
All right, what's anything to the 0 power? X plus 1 to the first power. Okay, x plus 1 to the quantity squared. Okay. X plus 1 the quantity cubed. X cubed plus 3x squared plus 3x plus 1. And Caleb, what's next to the board?
I got x to the 4 plus 4x cubed plus 6x squared.
Okay, I wrote it to kind of give you a hint.
We are doing that.
Some of you didn't need the hint. But those coefficients are what numbers?
That one dude, Cameron.
Say it louder.
Pascal's triangle.
Pascal's triangle.
I feel like that one dude's Cameron is more descriptive.
It is, yep.
It's not.
Okay, Pascal's triangle. What's the pattern in Pascal's triangle? You take a number and you add up the two diagonal to it. So 1 plus 2 is 3, 3 plus 3 is 6. Here there's 10, 4 plus 6 is 10. Okay, so if 1, 5, 10, 10, 5, 1 is that fifth row, then the sixth row would be 1, 6, 15, 20, 15, 6, 1, etc. Okay, you may recall from last year in Algebra 2 that these actually describe the coefficients. Let me tighten text to redo my projector there. They actually describe the coefficients of x plus y to the n power. Okay, instead of actually having to do multiplication 4 times, if we had x plus y to the 5th power, we could just come here, and these are the coefficients for each term. Now, do you think that it's efficient for you to memorize the triangle? Probably not. Okay, so there is another way that we can get the coefficients. Okay, we all just hold on. We also need to know the pattern of when do we have x to the 5th, and when do we have x to the 4th, and when do we have y cubed, and that kind of thing. Okay, so if you have a binomial to a power, what does a binomial mean? Two numbers added together, a binomial. There are two numbers in your polynomial. If you have a binomial raised to a power, then you can use this formula. I'll give you a moment to write it down before we actually discuss what it means. Okay, so basically what you are going to do is you're going to use this combination formula to get each term in your expansion, okay? If you have something raised to the 5th power, instead of doing 4 distributions, because you know that that gets long and tedious, and there's a lot of room for error, we could use this right here. Okay, so if this were a 5, this were to the 5th power, we'd start here with 5 combinations of 0. And then x to the 5th, y to the 0. And then our next term, we would move to 5 combinations of 1, x to the 4th, y to the 1. And then 5 combinations of 2, x to the 3rd, y to the 2nd, etc., etc. Okay? What's going to happen, this is always going to be whatever this number is. You're going to start with 0 here, and then you're just going to increase by 1 with each term until you get to n combinations of n. okay? These exponents right here will always add up to be what? N, okay? So if n is 5, your two exponents should add up to 5 for all of those, okay? And whatever numbers right here in your combination will match your second exponent in each of the terms before you simplify, okay? And that's it. All right, now, I told you that the coefficients were Pascal's triangle. Now I'm telling you that there's these combinations. Well, guess what? Pascal's triangle is just this. And you don't need to write this down. But all those numbers in Pascal's triangle come from the combinations for each integer. Isn't that cool? I see that you're blown away. Okay, and this is kind of there. So like this, I call this the 0 row because it's 0 combinations of 0, okay? But like here in the fourth row, 1, 4, 6, 4, 1, we're going to use in our work 4 combinations of 0, 4 combinations of 1, 4 combinations of 2, etc. Instead of having to write down Pascal's triangle every time we need to multiply something out, we're just going to remember this pattern of the combinations. Okay, it'll be easier for us and more efficient. So basically what you're going to need to be able to do is set up the expansion using that formula, and you got to be able to use your calculator the right way. That's pretty much it. Okay, so we're going to do a couple examples, and since it's Friday, I'll give you some time to work in class. Now, your calculator does have this capability of finding n combinations of r. But this is how your calculator finds it, right? We might have talked about this in the probability video. Yes or no? Yes, you talked about combinations and permutations in that video. It's been a while, I remember. Okay. What I want you to be aware of is that sometimes you will see it written as this right here. Okay? Not necessarily something that you would need to know this year. Oops. But if you go on to further math classes, I need you to be aware that this is the same notation as in combinations of R. It means the same thing. Okay, so let's just make sure our calculators work. Get them out. Okay, get your calculator. Make sure that you can find 8 combinations of 2. Yes?
On my calculator, there's a shortcut. You hit alpha, window, and then it pops up
Alpha window. If you have an 84, hit alpha window.
Where's alpha?
Sorry, dude.
What's it supposed to be?
What is 8 combinations of 2?
I can get to that 34.
28.
28? Way better than having to write out Pascal's triangle and figure out what that number is, right?
But what if you have just like a lot of problems like this? Could you just do
What does this mean?
too many combinations of 3?
This is the same thing as 10 combinations of 3. Find it. What? Don't you love community tricks? The 83 is not going to have it at all. The 83 does not have two cuts.
Is not in scroll. Look at that. Scroll over.
Okay, I have 3 examples. Are you ready? 3. Oh, I lied. We have 4. We have 4 examples. We have 4 examples. First example, pretty tame. 2x minus 3 to the 4th power. Okay. First of all, let's consider that before today, you would take 2x minus 3 times 2x minus 3. And then you take that times 2x minus 3. And then you take that times 2x minus 3. Oh my gosh, how do you feel about that? Kind of a pain in the rear, right? No, you don't think so? No, it doesn't bother you? Okay.
Now if you get 6.
Is there a lot of room for error when you're multiplying that many times?
Yeah, I mean,
There is a lot of room
on the
for it.
roller coaster project,
Last year,
I would do my math in 12 months.
That's what we're doing.
Just show us.
That's what we're doing. Yeah.
Oh my.
Okay, so let's go through it, Caleb, so I can show you how Mr. Griebel and I are on the same page, okay? So n would be 4. We're raising to the 4th power. So our first term is 4 combinations of 0. In your binomial, we have 2x and minus 3. So 2x gets raised to that 4th power, and negative 3 gets raised to the 0 power. Notice how 2x in its entirety is being raised to the 4th power. That 2 has to be raised to the power as well. Okay? Then your next term, you're just going to move on down the line. Now we have 4 combinations of 1. What happens to the power of 2x? It decreases to 3, and then negative 3 will now have a power of 1. Yeah? Same thing? Okay. Then we'll move to 4 combinations of 2. 2x will now be raised to the 2nd, and negative 3 will now be raised to the 2nd. Notice how my exponents are adding up to 4, and whatever is on that second term, that exponent matches the number in the combination. Four combinations of 3. 2x is now being raised to the 1st power. Negative 3 would be raised to the 3rd power. And then last, but certainly not least, 4 combinations of 4. 2x to the 0, negative 3 to the 4. Once we get to n combinations of n, that is our last term. We can't do anything else. Okay? So now it's just a matter of punching numbers. Okay? So some of you may not need your calculator for this problem. Some of you know that row in Pascal's triangle. If you don't, you have a calculator, it doesn't matter. What is 4 combinations of 0? What is anything combinations of 0? 1. Okay. 2x to the 4th would be 16x to the 4th. And then negative 3 to the 0 is 1. Some of you may choose to do this all at once and just go straight to, okay, my first term is 16x to the 4th. But I'm going to write it out step by step so you can see where each number is coming from, okay? Our next term, What is 4 combinations of 1? Four. 2x cubed. X cubed. Then we have negative 3 to the first, which is negative 3. Eli, what's our term?
Negative 26.
Good. 4 combinations of 2. That's 6. 2x, the quantity squared, would be 4x squared. And negative 3 squared is 9. Please do not rely so heavily on your calculators that you put negative 3 squared as negative 9. You know that's not right. Avoid using your calculator for simple calculations like that, please. What's our third term?
16x.
Okay. 4 combinations of 3 is 4. You'll see that pattern, right? It's symmetrical. Those combinations are symmetrical. 2x to the first is just 2x. Negative 3 cubed, negative 27. So our fourth term is what? Negative 216?
Negative 216x.
All right. And then we have 4 combinations of 4, which is 1, 2x to the 0, which is 1, and negative 3 to the fourth is a positive 81. Please be careful with that. And there is our binomial expansion. It's exciting, right? We didn't have to multiply any binomials together.
Chris,
Questions? All right, I am going to give you 2 minutes to write this down and just set up each term. Don't figure it all out. Just write it down and set up each term. No, you start out there. Well, x squared is going with Does your 4 terms match mine up here? It begins with 3 combinations of 0. Our first term is x squared, so x squared gets raised to the third, and then 4 to the 0. 3 combinations of 1, x squared squared, 4 to the first. 3 combinations of 2, x squared to the first, 4 squared. 3 combinations of 3, x squared to the 0, 4 cubed. You are going to have terms that may have a power inside of your binomial. You still treat those the same. That term, in this case it's x squared, here gets raised to the third power. So yeah, we are going to have x to the 6th as our first term. That's fine. We're taking x squared times x squared times x squared. That makes sense. Three combinations of 1 times 4 to the first gives us what number? No. Times 4 to the first? Be 12, right? 4 times 3, we'll just put yours together, 2 answers. Okay. 3 combinations of 2 is 3 times 4 squared, which is 16. 16 times 3 is, we have 48 x squared, and then plus 64. Some of you may not need that step in between, like I did up in this first example. A lot of you are going to be able to set it up and get to here. Now, at the very least, I need to see the work that I have up here in green. If you just come up with this answer, I'm not going to accept it for full credit. I need to see where you're getting those numbers. I get that some of you may feel that this is tedious. However, if there's a mistake, we can fix it, all right? If you're maybe not putting the parentheses in the right place, or you have it set up correctly, but you didn't punch it in your calculator, right? I can at least give you partial credit for the correct setup, okay? But I want to be able to help you if it is wrong. And I want to be able to see where that mistake happened, whether it is calculator user error or pencil user error. Okay. Now, I am not going to give you x plus y to the 12th power. That's not really fair. Okay, that is tedious. But I could ask you for the 6th term of a really large expansion. Go ahead and write down the example. Do not start expanding this. Not worth your time. There's patterns here. Math is full of patterns. It's one of the reasons why I love math. Okay, so let's pick up on a pattern here. If I'm looking for the 6th term, since we have an expansion that is to the 8th power, I know I'm going to begin with 8 combinations of something. What is that something?
6.
I'm hearing 5, I'm hearing 6.
Go 5.
Okay, our first term always starts with n combinations of 0. So if I want my 6th term, our first term is 8 combinations of 0. Our second term, 8 combinations of 1. Our 6th term would then be 8 combinations of 5. Okay, well then where do we go from there? We know A needs to be raised to a power, and we know 2B needs to be raised to a power. We know which of those 2 powers. Well, we know both of them, but this 5 should match which power? Okay, whatever your second term, whoops, you said 2B, I wrote 2B. Whatever your second term is in the binomial, that power will always match what you have in your combination. And then, since we know the sum of those powers need to be 8, if this is 5, then A is going to be raised to the third. What's 8 combinations of 5? 56. So we have 56 times a cubed times 32 b to the 5th. 56 times 32 would be okay. Now that's not so bad. Right? It's really not a lot of work. Last but not least, ready guys? Last example. Okay. Go ahead and write it down. Find the coefficient. Find the coefficient of the term e to the 6, e to the 5. Write it down. Don't do anything else. Okay, so our term, since this is 11, we have 11 combinations of something. We know we need 3a raised to a power and negative 2b raised to a power since it is subtraction. Now, we know the exponents. We know that a needs to have a 6th power, and we know b needs to have a 5th power. So how do we fill in our combination? 11 combinations of 5 because it has to match that second exponent. Okay, so we need to take, help me out here, what's 11 combinations of 5? 400 and what? What is 3 to the 6th? So our term would be negative 10,777, negative 10,777,536, a to the 6th, b to the 5th. That's all fine and dandy, but what did they ask for? They asked for the coefficient. Well, you better give them the coefficient. The coefficient, all I want is negative 10,777,536. That's all I want. Negative 10 million.
We're done. I just want to small. I just want small.
On school.
Too bad it's late.
Okay. Your last book assignment. Oh, good. Here. I can't remember what our
I'll be
is.
here because
Yeah, we
They
get
better
it.
not speak too fast. Okay, it's not the last time you'll use the book, but it's your last daily assignment from the book. We're going to use our book for a final review.
This sounds
Yeah.
late.
Yeah. So we have 8 minutes left in class. I challenge you to get 2 problems done before you leave. 1, 2, 3, go.
How you gonna get problems on without the book?
No, you don't.